All right, everybody. Thank you all for attending the latest of our remote series of high energy seminars. We have one speaker today, Peter Breiding. Um, Peter recently started a postdoc at Johns Hopkins, where he's studying the most powerful high redshift Z greater than 1 radio galaxies, which belong to the 3C radio galaxy sample, with deep broadband HST with 3 IR UV observations. He received his PhD in 2018 from the University of Maryland, Baltimore County, with Eileen Meyer as his thesis advisor. And that thesis focused on the multi-wavelength observations and analysis of kiloparsec scale X-ray jets in AGN. His previous position after his PhD was a postdoc at West Virginia University, working on observations and analysis of binary supermassive black hole candidates under Sarah Burke-Spolaire.
Yeah.
So without further ado, thank you for joining us.
Hi, it's great to be here. Can everyone hear me?
Yeah, just fine.
Yeah, so today I'm probably going to be talking a lot about radio astronomy, and hopefully that's still of interest to the high energy seminar that I'm with today. So the first obvious question is, why study binary supermassive black holes? First off, just to get everyone straight, we believe that most, if not all, galaxies harbor a supermassive black hole in their center. And furthermore, there seems to be weird correlations that are not explained between the mass of the central black hole and various host galaxy properties. So on the bottom left, I'm showing the famed M sigma relation, where there's appears to be a correlation between the black hole mass in galaxies and the stellar velocity dispersion of the bulge stars in the galaxy. This is weird because this is the bulge is well beyond the gravitational sphere of influence of the black hole by many orders of magnitude. And there's various other host galaxy properties that correlate with black hole mass, including the bulge luminosity and mass and other things. So we don't fully understand how this M sigma relation came about. One avenue to explore to try to understand the correlation and the overall relationship between galaxies and their black holes comes from looking at the problem through hierarchical merging scenarios. So in some lambda CDM models of cosmology, you have large-scale structural formation through the merging of galaxies and major mergers, and this can be several times throughout cosmological history or more. So the idea is through the merger of galaxies, inevitably you will get the formation of binary supermassive black holes, as the two black holes in each merging galaxy are brought towards the center of this merger. And other interest, so this is one way to grow the mass of galaxies and black holes and to study the relationship between the two things. And this may or may not trigger AGN or quasar activity, which could help regulate these properties through feedback. And I'll talk a little bit more about AGN later. But as a precursor, we know that there's a lot of interesting things that the binary can do on the properties of this host through the observation and simulations of this scouring of stars in the bulge. You see this deficit of stars due to the black hole activity. So finally, as the binary gets close enough, they emit gravitational waves. And these gravitational waves are actually detectable using different methods. So the planned LISA, a laser interferometer space antenna, is planned to be launched, and it's going to operate similarly to LIGO, but it's going to be looking for massive black holes, typically in the order of thousands to tens of thousands of the mass of the sun. And then you have pulsar timing arrays, which have been operating for the last few decades. These are sensitive to much more massive black holes on the order of millions or billions, really, of solar masses, and very nearby binary black holes. So pulsar timing arrays, they work by the timing of millisecond pulsars. So millisecond pulsars, these are neutron stars in a binary that have been spun up through the interaction with a stellar companion, possibly a red giant. And as they the pulsar timing arrays and nanograv is the nanohertz North American Gravitational Wave Observatory that uses the Green Bank Telescope in West Virginia and formerly Arecibo in Puerto Rico in order to time the pulses from these pulsars within the galaxy. And they're looking at dozens of pulsars in our galaxy, and they time the pulse arrival times with these pulsars down to the microsecond root mean square sensitivity. And they look for deviations from they use physically motivated timing models, and they compare the pulse time of arrivals with their timing models in order to look for any correlations in the residuals from their timing models that could be indicative of a gravitational wave, a very long wavelength passing through the galaxy over the pulsar and over Earth. In the bottom left, I'm just showing an example of a very strong, exaggerated signal from a close by supermassive black hole binary. And you can see different colors or different pulsars. And they actually probe different phase space for the gravitational wave because they're located at different distances from us. But back to binary supermassive black hole evolution, when you have a galaxy merger, dynamical friction is the process that brings the two black holes to the dynamical center. This takes on the order of 100 million years. Then from the scale of 10 parsec to subparsec separation, you have what's called the final parsec problem, where the three-body interaction with stars in the galactic center, along with circumbinary accretion disk torques, maybe a third supermassive black hole interactions in order to steal or remove angular momentum from the binary until it can enter the gravitational wave dominant regime that nanograv is looking at in pulsar timing arrays. When you reach very, very subparsec separations, and this drives the evolution until the eventual coalescence. But the interesting thing is the parsec scale binaries is where you have this final parsec problem. So depending on how efficient this binary evolution is during the final parsec problem, you could lead to a lot of close by binaries that are strong gravitational wave emitters that we can look for the gravitational wave signal from, or a deficit. So in this plot, I'm showing the strain versus frequency for different models of binary evolution. And you can see the green is optimistic, blue is the pessimistic. Depending on how efficient that final parsec problem process is and the different properties of these galaxies, the upper limits from the PTA non-detection, which are shown as the black curve, is starting to eat into that parameter space. So we're getting close to making astrophysical constraints based on pulsar timing array observations already. And this era of multi-messenger science is just beginning, basically. So how can we find the binary supermassive black holes at parsec separations to try to help inform PTAs and this multi-messenger science? So there's a few methods. I'll talk about two main ones. All of the methods basically rely on the phenomenon known as active galactic nuclei. So in this paradigm, you have a central engine of a supermassive black hole with millions of billions of times the mass of the sun. This accretes, there is an accretion of matter onto this black hole and what's known as an accretion disk. This is the central engine, what's powering the supermassive black hole. This accretion disk gets really, really hot. It glows very brightly at optical UV radiation, and the UV radiation excites emission lines in what's called the broadline region of gas clouds, rapidly orbiting the black hole within 1/10 of a parsec. And these AGN can even, in some cases, produce relativistic jets that can extend well beyond the scale of the galaxy, all the way up to megaparsec scales in the most extreme cases. So using AGN, one method of finding binaries is to look for the periodic modulation of AGN light curves. So the idea here is the binary can influence through the periodic motions of the binary can influence either the accretion rate or various other mechanisms can lead to the periodic modulation of the light curve output. And typically in history, this has been observed as periodic modulations with optical facilities, time domain facilities such as the Zwicky Transient Facility or Catalina Real-Time Transient Survey. And this is sensitive to binaries that are very subparsec, so well within the nanograv pulsar timing array regime, when you have the gravitational wave regime, and orbital periods on the order of days to years, dictated, of course, by the cadence of the observations. However, this method suffers from alternative possibilities for introducing this variability, including just stochastic variability that you're misconstruing as actually periodic, various MHD instabilities, et cetera, can lead to these periodicities. So the method I'll focus on today is the Doppler shifting of broadline region emission lines. So if you have a broadline region, clouds attached to one of the black holes in the binary, you can observe these offset emission lines as the binary executes its orbits around the center of mass. So for this sample, the Iraklis et al. 2012, there is the observation of offset broadlines in the H beta profiles of 88 out of 16,000 SDS quasars, all redshifts less than 0.7. So you can see the optical spectra in the bottom left. The dashed line in the center marks the narrow line region center of the narrow line region gas clouds that trace the rest frame of the galaxy. The dotted lines mark plus or minus 5,000 kilometers per second. So you can see these offsets are on the order of a few thousand kilometers per second. Now, this method favors binary separations in the order of 0.1 to tens of parsec, so well within the final parsec regime, basically. But again, there are alternative models that can explain these offset broadlines. One of them being you have a recoiling supermassive black hole. So after the merger of a binary, you can have the anisotropic emission of gravitational waves that gives a velocity kick to a black hole. This favors velocity offsets on the order of a few hundred, but can extend up to a few thousand kilometers per second. And this can lead to kiloparsec scale offset AGN if that recoiling black hole stays active for long enough. And finally, you have broadline region gas outflows, that systemic outflows of the broadline region gas, possibly induced by a relativistic jet, possibly induced by an accretion disk, can lead to these systemic velocity offsets. So how can we test these different models? With high resolution radio imaging is the punchline. So we skip over this. With the very large array in New Mexico and the very long baseline array, we have a series of observations that took place in 2013 and 14. So the very large array probes angular scales from arc seconds to arc minutes, or physical scales 100 to tens of thousands of parsecs. Very long baseline array, which is an array of 10 radio dishes across the continental US, probes milliarc second to arc second scales, so sub-parsec up to hundreds of parsec scales. So we had a very large array finder survey, and it essentially defined which of these binary supermassive black hole candidates were radio loud, radio emitting, and were good sources to follow with very long baseline array observations. So in this VLA finder survey at 10 gigahertz at A configuration, so beam size or angular resolution of a tenth of an arc second roughly, we found 59 out of 88 of the sources were detected, and they are mostly unresolved point source detections. So if we're looking at the morphology of a radio loud AGN, you have the core, which is a region at the base of a relativistic jet produced by the black hole. You have the relativistic jet itself, and then you have these radio lobes that are, in this case, what's called an FR2 radio galaxy, where the jet is impinging on the intergalactic medium, creating these bright hotspots and these puffy isotropic lobes where the plasma is non-relativistic. So if we look at the radio spectra for these different features, for the core, you expect it to be what's called synchrotron self-absorbed. Basically, the optical death has reached unity. So you lead to this turnover in the spectrum where you expect to see a flat radio spectrum. The jet and the lobes have progressively steeper radio spectra owing to radiation losses and optically thin emission, essentially. So I'm showing on the left here the radio spectral index histogram taken with the VLA with multi-term, multi-frequency synthesis in band imaging analysis. So basically we determine the spectral index just using that one radio band, and most of the objects do cluster around a flat or inverted spectral index that you would expect for a radio core of an AGN. The bottom left, I'm showing the signal to noise plot. So this method is really good only when you have high signal to noise detections of the point sources. Now, I discussed previously that you might expect to see a correlation, or maybe I didn't. You might expect to see a correlation between the brightness of the radio source as a function of the broadline velocity offset if we're dealing with a jet-induced outflow scenario. And this is due to an effect known as relativistic beaming. The more closely you align a relativistic jet to the line of sight, the stronger the radio emission is due to Doppler boosted or relativistically beamed radiation that's focused along the axis of the jet. So if you plot all of these sources together on a luminosity versus velocity offset plot, which you can take to be the blue circles and red diamonds here together, you see no correlation, but there's hints of a correlation if you just take a cut on the inverted and flat spectral index sources, which are possibly a core of some AGN. But this is a preliminary analysis, and I'm going to discuss the VLBA observations next. So with the VLBA, the hope for the signal of a binary might be, as I said before, to see two flat or inverted spectrum radio cores indicative of the region very close to the central supermassive black hole central engine. So we imaged the 34 brightest of those VLA detected sources with the very long baseline array at X band again. And I'll skip over this. The punchline is that we only find single point source detections for all of them, but this doesn't rule out the presence of a binary. The spatial resolution for these observations is down to roughly 10 or so parsecs. So that's not cutting into the subparsec separations that we could be expecting. And we plot, I show two plots here, the offset between the VLBA and Gaia source positions. So you might be able to interpret various physical properties. If you see any statistically significant offsets, we find offsets from the radio optical positions on the order of 10 parsecs for 3 sources, but we can explain that in a variety of different ways that doesn't distinguish between a recoil scenario or binary AGN or other things. So there's more interpretation is needed there. So we completed follow-up VLBA observations at Q band, so 5 times higher frequency for the 4 brightest targets. And these observations were in order to probe much smaller angular scales, 5 times smaller angular scales, and better sensitivity to inverted spectrum cores. And we have Hubble observations for those same objects in order to look for precise radio and optical host center offsets. The idea here is we can look at the actual galaxy's light profile by subtracting the quasar's PSF from the host and actually find the host center where we're not contaminated by the light from the quasar. And we can also look for evidence of a merger, as in tidal tails or asymmetries in the host galaxy after the quasar PSF subtraction. And we have XMMNewton observations that we submitted a proposal for. And the idea for these observations is multifaceted. One of them is in order to measure the mass of the accreting supermassive black holes through correlations with various properties such as the normalized excess variance with the Eddington ratio, with the black hole fundamental plane. And the idea is if we have an accreting supermassive black hole in the binary that's much less than what one can measure through the host galaxy correlations, which measures the total black hole mass, we might be able to find evidence for the binary in that way. And then also with the X-ray observations, we want to do X-ray spectroscopy in order to possibly test the BLR outflow hypothesis, with the idea being if we could detect the iron K alpha line from the accretion disk in some subset of these objects, that would probe a rest frame commensurate with the black hole, while if you have a BLR outflow hypothesis, the rest frame of the systematic BLR outflow would be different from that of the rest frame of the black hole. And we could look for those velocity differences in the iron K alpha lines relative to the broad lines. I think I'm beyond my time limit, so I could skip this next piece.
You're the only speaker today, so if you want to go a little bit longer, that's fine.
Okay, I can finish up. So I will present some results. We looked at the binary supermassive black hole candidate NGC 7674 with VLBA and European VLBI network observations. So NGC 7674 is a Seyfert galaxy. And in the center, you can see in the middle image, you can see the kiloparsec, actually it's 1 kiloparsec in extent radio jet, which has an S or Z shape morphology. The interesting thing about this type of jet is the S or Z shape could be induced by a binary supermassive black hole, where you have a jet precession due to the binary, and that can lead to that type of morphology. So back in 2017, Carbadal presented a KU band 15 gigahertz VLBA observation where they supposedly detected 2 radio cores of this binary, and there are 2 inverted spectrum cores based on a non-detection at lower frequency. So it would be the closest binary ever directly imaged, both in physical separation of the binary and closest to us in redshift, if it was indeed correct, using a variety of different epoch observations and different frequency observations with the VLBA and EVN. We looked for the evidence of this binary. The punchline is we didn't find it. On the right, I'm showing a SED for both of these cores. The red upper limits are from non-detections from our imaging. The black flux density is from the CARB 2017 detection with arrows on the spectral index showing the spectral index limits based on their non-detection at X band. So you can see using multiple different epochs, multiple different frequencies, we don't see evidence for this binary, unfortunately. And this is based on a whole host of data in 2002 and 2018 with both the VLBA and EVN. And you can see some of the features from the kiloparsec scale features. You see on the right, I'm showing the VLA observation at KU band, where you can see C and W are hotspots, so where the jet's hitting the, in this case, dense ISM, because there is also some evidence for jet ISM feedback in the source due to Doppler shifted absorption lines. But in this case, you see C and W with the VLBA observation, the VLBA observations from this analysis. You can see both of those features. And in each of these images, we're showing the non-detection, no evidence for the binary. And you can see on the bottom right, I'm also showing the spectral index map for the source, where interestingly, you do see an inverted spectrum where the binary should be, which again, inverted spectra could be evidence for a synchrotron self-absorbed core of an AGN. But in this case, it's also possible it's due to free absorption. It can also give you that type of signature. So it's an interesting source, but we don't see evidence for the binary, unfortunately.
All right, thanks, Peter, for a great talk. We already have a question in the chat, and we can also take questions by the raising hand function. First question is from Magdalena. Do we have an estimate of the spread of AGN disk scale heights?
No, I don't think so.
Okay.
But I can recheck the various theoretical modeling papers on this sample for that. I'm not aware of it though.
And Dan, you have a question?
Yeah, hi Peter. Nice to see you again. Looks like this is your first day in your new office.
I don't have any books here yet.
I'm wondering what would be a smoking gun, no argument. This is a binary black hole measurement.
Yeah, I think a smoking gun will be whenever nanograv gets beyond the, well, first the stochastic gravitational wave background detection. When they get to continuous wave detection, and you can corroborate that, you can corroborate, say, a PTA detection of a binary source with electromagnetic evidence, that would be two completely, you want multiple independent lines of evidence that leads you to a binary. So for the case of what people count as one of the best evidence for a binary from this VLBI observations is this guy here. this CSO 0402 candidate, you can see C1 and C2 are two flat spectrum cores that they imaged at multiple frequencies. They also did proper motion tracking for this object, where they found evidence for a binary based on its proper motions. So I think you want multiple different lines of evidence that are all going in the same direction.
If I can keep asking, I don't have any feeling for, what fraction of galaxies should have binary or multiple black holes. Is that a well-measured quantity or a hypothesized quantity?
So I think that there's a lot of different results you can get from simulations, but it's not well constrained yet. So that's one of the things, that's something that PTAs are going to be doing, obviously, in their analysis. It's helping constrain. Where is that plot? This plot right here. So there's different types of models that give you different types of, this is all population modeling. So depending on the type of model you're using, you get different answers for what the, say, characteristic strain from the ensemble emission of binary supermassive black holes should be. And PTAs are helping constrain that. But EMs are, what should I say? Not commensurate different modalities should be used. So this periodic light curves, these offset Doppler shifted broadlines. There's other methods too that I didn't talk about besides these two. These are the two main ones that people talk about. That's why I talk about them. But there's a whole host of different methods you could use, including one recent one with Gaia astrometry, looking for astrometric excess noise.
Yeah, I'm asking because I'm with a group that's doing X-ray astrometry with lensed sources. And, we only have 10 or 20 or 30 objects. So I don't know if and we think we can measure 8 parsecs at high redshifts. But I don't know if we should expect half of them to be binary or only 1% of them, which means we wouldn't measure any.
No, yeah, ruling out lenses versus binary is an interesting point to make. Yeah. So when there's some surveys and searches for pure VLBI data where you can see doubles, perhaps, but that doesn't necessarily tell you that it's a binary. It could be a lens, for instance, like you just said, or something else.
Brandon?
Okay, sorry, I got myself unmuted. Yeah, I was curious about how you're setting your selection criteria. You're setting a limit on flux and then taking everything above that. What motivates exactly where you set that marker for your analysis?
For the VLBA observations?
Yeah, I think there are a couple spots where you're taking flux cuts effectively, and I was just curious how you set that or how you investigate the effects of that cut.
Yeah, so let's see. Yeah, so we did the parent sample is directly a sample of 88 objects from SDSS. So there was the VLA observations that had a certain percent radio detections. So yeah, that's essentially a flux cut and then a flux cut again. Those VLA observations are all to the same flux limit. The VLBA observations are just of the brightest objects because it's very prohibitive to go to lower. Once you start getting to those lower flux densities, you're getting to prohibitively long integration times of the VLBA.
So you're setting essentially an observation time limit, and anything that falls below that, you're not trying to observe, is what you're saying.
Yeah, for the VLBA, at least it just becomes very prohibitively long in order to try to observe deeper sensitivities. But so we dealt with this in the paper, and I don't have a slide on this. Basically, for these binaries, you have a few different possible scenarios. You have the scenario, okay, our angular resolution wasn't fine enough. So we could have a binary that's still within basically the beam size of these VLBA observations that's just unresolved, right? Or you could have the possibility where you have a secondary that's really radio faint. And the way that we dealt with that is we looked at we used the radioluminosity function for nearby flat spectrum AGN. And we basically use that in order to put a probability on their existing or radio faint companion that went undetected due to the flux limit of those observations. So it's in the paper. You can look at the different probabilities for that. Some of them, it's very well ruled out that you have radio faint companion. Some of them, it's not. But then there's also the additional question, okay, you could just have a non-radio emitting black hole. This entire analysis relies on the idea that both of the black holes are radio emitting, right? So you could just have one radio emitting black hole, one that's not.
Oh, sorry. Thanks. Yep.
All right. Any more questions? If not, then let's thank Peter again for a great talk. We have a sign-up sheet for him spread by email. Dan, did you raise your hand or is that a clap? Okay. Yes. So there's plenty of time, I believe, this afternoon and tomorrow morning. So if you want to speak with him further, sign up there.